record to the cloud. I don't need a transcript, thank goodness. So we are continuing our discussion of precision for planning today, and we're going to start talking about correlation, everybody's favorite thing. Oh, that's not good. Oh, I know what I'm going to do. I give you the notes in full. Why don't I just pull up Google Chrome and just do it that way? Because I have to have all of these USB ports occupied. I got no room for nothing else. Nothing else fits. Okay. Thanks for being patient, y'all. All right. All right. Oh, we're not talking about drugs and behavior. Okay, syllabus and course documents. Let's go ahead and pull up those slides.
Are you tripping? LSD?
No.
Tripping?
No, not really. I would never. I'm not look, I am not one of those people who really likes to be out of control of myself. I would never. You really don't. I'm the most boring person alive. I'm really not that interesting. Sorry. Okay. I wanted to pull this up because I've only got 2 USB ports here and they need to be used for the camera and the mic. So that's why I spent all this time doing this. Okay. So here we were kind of talking about planning for power with different types of groups. So remember that there are a couple of different things that you need to know. If you want to be able to plan for certain types of power, this will help you figure out how much power you have based on the number of people that you have in each group and the target effect size that you want. So what you're looking at here are deltas of 0.8, 0.6, 0.5, 0.4. We have the size of people in each group, and then we have our measure of power here in orange. So you can actually follow along with these figures in your book. Now, as you kind of see, more people in each group is generally going to be better for your power. Additionally, if you are looking for an effect size like a Cohen's d of 0.5 or more, you're going to have more power, especially with more people. One of the things that you will notice, though, and this is kind of the relationship between our alpha and our power level. So notice here, when we have an alpha of 0.05, let's say that we're looking for a Cohen's d of 0.8, and we want maybe 40 people. Notice that here we have a power of 0.94. On the other hand, if we have an alpha of 0.01, so if our type 1 error rate is smaller, if our alpha is smaller, our power becomes less. For a Cohen's d of 0.8, 40 people only yields a power of 0.82. So there's always going to be a trade-off between your alpha and your power. The smaller that your significance level is, the less power that you have. Because if you're making your if you're making sure that you don't have as many type 1 errors, you are then going to run the risk of having a larger likelihood for type 2 error. Now, one thing I did want to mention just as a reminder, so if I have an alpha of 0.05, if I have about 30 people in each group, and we're looking at a Cohen's d of 0.5, that gives us a power of 0.48. What this tells us is that we basically have a little less than a 50% chance of finding statistical significance if a medium-sized effect actually exists. So I don't know about you, but 50% is not good enough for me. I hope it's not good enough for you either. So what this means is that generally the average power to find medium-sized effects in a lot of research fields is around 50%. That means about half of these studies would fail to find statistical significance by chance alone. And so power is really critical, and it goes without saying that even in my field of cognitive psychology, many research studies in psychology are underpowered. We don't have enough people in our data. And this could be that because when you are focused on null hypothesis testing, remember that your type 1 error rate becomes far more important. You want statistical significance and you don't want a false alarm. So as a result, we tend to overlook our type 2 error rate. Now, if you have a paired design, you get more statistical power. Now, with a paired design, we need to also consider the population correlation between our, remember that the population correlation coefficient, it's right here. That is the Greek for R, that is rho. So here, what you can kind of see is that the more highly correlated that your two measures are in a paired design, the more power that you get. Additionally, the more people that you have in each group, or not in each group, but the more people that you run, the more power that you have. So here we have a top panel where rho is 0.6. So if we have a pre-test and a post-test measure, they're about 0.6 correlation. Here we have a pre-test and a post-test measure of 0.8. And you can see that in general, power tends to be greater when our paired measures are very highly correlated with each other. So here's the thing, we don't always know what rho is. So you have a couple of different things that you can do. If you don't think they're very highly correlated, select a rho of 0. That basically means that they're not correlated at all, and you are effectively reverting back to an independent group's design. On the other hand, most pre-test and post-test measures or paired measures often have at least a 0.6 correlation. It really benefits, and I would recommend if you're interested in this kind of thing, that you look back on whatever it is you're studying and look at what correlations previous researchers in your field have obtained. And ideally, what I hope you're noticing here is that in general, if you want to increase your power and you've already got your measures set up ahead of time, the best thing you can do is add more people. That is always the easiest thing to do. So here are a couple of things to kind of keep in mind, and you should have a good strategy. Your target effect size, your Cohen's d or your delta, is influential. Larger effects will give you more power. Don't go chasing after small effects. There's a very high likelihood that for a medium-sized effect, even with a large number of people, you only have about a 50% chance of getting a significant effect. Additionally, your type 1 error rate, characterized as alpha, is influential. Lower alpha, so an alpha of 0.01, means it's going to be harder for you to reject the null. So that means you've got a greater likelihood of type 2 errors, missing things that actually exist, and it means lower power. So obviously, your group size is influential. In general, bigger numbers of people yield higher power estimates. For the paired design, rho is influential. A larger rho gives larger power. So larger rho requires smaller n for the same power. So if they're highly correlated, what luck? You need even fewer people with a paired design, and that's pretty cool. So there are a bunch of things that you need to consider when you're trying to plan for a study. So how should we choose the target effect size? So there are a couple of different things that we can do. You could be guided by past research, and I would recommend that that's probably going to be your best bet. You could guess what the true value is, but if you're new to this, you're not really going to have those intuitions. Even I don't have those intuitions. I'd rather look back and see what other people have done. You could use Cohen's small, medium, and large conventions that we talked about a while ago. But generally, you might want to explore a few different values so that you can kind of see what the trade-offs are among your sample size, your target effect size, rho, if you're using a paired design, and a power, all for a particular alpha level. And generally, choosing your number of people for a study is always going to be a matter of judgment. And I would say that in general, when it comes to replication, one of the best things that you can do is go back and look at original studies. If you're trying to replicate a study, here are some guidelines for you. This will help. In general, if your original study is the original study that you're trying to replicate has 35 people in its sample, how many people should you have in your sample? At least 35. You should try to match or exceed the number of people in the original sample. Additionally, you want to make sure that your margin of error, that target margin of error, is actually smaller than what was in the original study. Most studies are underpowered. So you should aim for a smaller margin of error than the original researchers found. Additionally, and you've heard me talk about this before, you want to make sure as much as possible that you need a margin of error that is at maximum half the size. At maximum, it needs to be half as big as the effect you want. So if I am expecting a Cohen's d of 0.8, my margin of error probably needs to be closer to 0.4 and probably smaller than that. Does that make sense? Okay. And I have this on a recording. You can come back and listen to this anytime you want. Okay. So I want to talk about something that a lot of researchers, myself included, have done in the past. And so I've certainly done this. It's actually possible for us to calculate power after conducting a study and use the observed Cohen's d that we get as the target effect size delta. And this is known as post-hoc power or observed power. So prior to this greater focus on replication, if you didn't find a significant effect in one of your studies, the reviewers when you send it out for publication, the reviewers will occasionally ask, how much power did you have? Is it possible that maybe you just didn't get this effect because you didn't have enough people? So oftentimes they would ask you to do a post hoc power setup. So here's the thing. The problem is that post hoc power doesn't really tell us anything because we are using the effect size that we obtained, not the one that actually exists. And because of things like the dance of the confidence intervals and the dance of the means, it's generally, because those things vary from replication to replication, our power will as well. We need to specify power ahead of time and not post hoc. For planning, we want to actually know the power that a study has to find a delta that we're interested in. So here's the thing, and you don't need to write all of this down. Post hoc power doesn't actually tell us anything other than what we obtained. It doesn't tell us anything new. It uses the information that we already had to reflect the results. Some software packages do report post hoc power. I actually used one called G Power. to basically report my observed power in a study, but generally you should avoid it unless they allow you to specify an effect size, because you're always going to be basing this off of what you obtain. So here we have 3 different simulated replications due to the dance of the means and the dance of the confidence intervals. Notice that our estimates of D vary, and as a result, post-hoc power varies. And notice too that your post-hoc power depends on the D that you obtain. So it doesn't actually tell you anything new, and you should try to avoid this. If you need help determining power ahead of time, come and talk to me. I can help, but don't do this. This is bad. All right, everybody good? Okay, so we're going to practice right now, and then we're going to take a quiz. So we're going to work together on this. So I want you to imagine that we have a student who is doing a year-long replication project and a research project. She wants to graduate with honors. So usually if you want to graduate with honors in psychology, this is the kind of thing they'll make you do, like an independent research project. So she has 3 different fields of study that she can choose. So let's kind of work through, we're going to help figure out which one is probably the best option for Angela to pick. So one possibility is based on using hypnosis to influence the Stroop task. Do y'all know what the Stroop task is? You look at different color words printed in different colors of ink, and they conflict with each other because reading is automatic, but naming ink color isn't, and you get kind of problems. You should have taken my cognitive class. I make everybody do the Stroop task at the beginning, and it's a lot of fun, and it makes everybody laugh. Look it up after class. It's cool. So it's a between subjects design. It's going to require 4 groups. Each participant is going to complete a 1-hour session. So the basic Stroop effect is large, and it's estimated that delta is 0.9. That's a pretty big effect. Another option is based on using economics education to influence sunk cost effects. For those who don't know, the sunk cost effect is basically when you are in a situation where you are not getting a lot of benefit. Like maybe you drive a clunker of a car and you keep putting thousands of dollars of repair into a car that is clearly old and needs to be replaced. It's the sunk cost effect. We keep using resources to justify something that's not really working out for us. It's a between subjects design that will require 4 groups, with each participant completing a 30-minute session. The basic sunk cost effect was recently estimated to be a moderate effect with a delta of 0.3. A final option is based on using social cues to alter the norm of reciprocity. If somebody does something nice, you do something nice back. This study can be run as a within subjects design, with each participant completing a 2-hour session. The norm of reciprocity was recently estimated to be a moderate effect with a delta of 0.3 when run as a repeated measure, typically an R of 0.75. So we're going to use ESCI, and I'm going to work with this together. And so we can figure out what our target size should be. So we need to make sure that we have a rule of thumb. We are going to obtain a margin of error at maximum that is half as big as the expected effect size. So that's what we're going to do. So here is how we're going to do this. So we're going to go into ESCI, and I didn't close out. I'm a winner. I love it when that happens. So we're going to go to ESCI chapters 10 through 16, and we're going to work through each of these to figure out which is the best option. Now, which would you pick right now, just reading through all of this? You picked number 3. Why? Okay. You know what I'd pick? I'd pick number 1. You know why? Because number 1 has the biggest effect, and it's more guaranteed I'll get the effect I want because of that. But that's just one piece of the puzzle. We have to consider how many people we'd need, how much time it's going to take. So we're going to go to precision 2, and then later we're going to go to precision paired. So our first study is between subjects design. So we have our Stroop effect is basically our delta is 0.9. So our minimum margin of error, or maximum margin of error should be 0.45. Now here's my question. Should we aim for assurance? Probably. We should probably be aiming for assurance here. So our target, I'm going to zoom out a little bit so that you can see, well, so I can actually move the slider, and then I'll get bigger again. We're going to move this slider to 0.45, and we're going to do this with 99% assurance. So notice that for this one, we'd need to have 53 people per group. So how many people is that total? We have 4 groups. We have 53 people per group. So how many people are we going to need minimum for the Stroop study? We're going to need 212 people. So that's the first one. And I would like to remind you, it takes an hour to run per person. So that is 212 hours of work. That is basically 8 days, almost 9 of work. And that's basically about 2 weeks if we're basing that off of a 5-day work week. Okay, so our second study is the sunk cost effect. In this case, our desired effect is 0.3, which means we're going to have to truncate this. I think we're going to have to truncate this because our target margin of error, y'all, is 0.15. Look at that. Okay, let me see if I can truncate this so we can see it a little bit better. Okay, folks, we would need 385 people per group for this one. I don't think we want to do that. So 385 people per group with a target margin of error of 0.15. Again, that's 4 groups. So 385 times 4. Anybody feel like running 1,540 people? 1,540 people? No? Okay, okay. And then finally, we have our norm of reciprocity. We have our norm of reciprocity here. Now here, it's 2. Now notice one thing I will mention with our sunk cost effect, we have 1,540 people, but they take 30 minutes to run. So this means it'd only take us 770 hours to run, which basically works out to about 32 days. 32 days of running. Maybe we don't want to do that. And then finally, we have our norm of reciprocity. This is about 2 hours. These are very highly correlated, but here's a couple of things we need. We need precision paired. I'm going to zoom out so that I can enter in these things. So our correlation is 0.75. And then our target margin of error is 0.15. Once again, we're going to make sure that we have assurance. And we're going to truncate this. Where is it? Why won't you tell me? Why won't you tell me? Wait, truncate. There we go. Okay. So with 99% assurance, we only need 117 people. Now, because this is a paired design, that's all we need. Oh, we need 117 people minimum. Now, they take 2 hours to run. They take 2 hours to run. So that's 234 hours total divided by 24 hours. That's about 9.75 days. So really, at that point, it is up to you. But can you see how I kind of worked through all of these a little bit? So when we look at our samples based on our precision tab, let me move my head. Okay, so when we do this here, the Stroop effect, there's 53 per group. So that's 212 people total. For the sunk cost effect, 385 people per group, meaning 1,540 total. With the norm of reciprocity, because it's a pair design, we only need 117 people. But now, here's what's critical. Angela is going to need funding. her university pays participants $10 per hour. So now we need to calculate the participant costs. So here's how we do that. Remember that the projects based on the Stroop task and the sunk cost effect have 4 groups. So in terms of how many people we need right now, norm of reciprocity is probably our best bet. In terms of cost, the Stroop effect is actually going to be our best bet. Actually, this is wrong. Let me go back. Let me see. Yeah, it's about 1 hour. So I mathed that wrong. So 212 times 10, because it's a 1 hour session. Let me fix that because it's going to bug me. So when we do this, once again, honestly, either the Stroop effect or the norm of reciprocity would be fine. You're only going to pay a little bit over $2,000. If you were hoping on the sunk cost effect because it's short, I have news for you. It's a pretty small effect. It's pretty hard to get. You're going to have 1,500 people and you're going to have to pay $7,700, like $7,700. So maybe we don't do that one. So now Angela's going to need time to run her study. So assume that each participant is being run individually, and we're going to calculate the time that it takes. So it's about 106 hours for Stroop. It's about 770 for sunk cost. That's about 19 work weeks. And then 234 hours for the norm of reciprocity. And that's 6. That's like a month and a half. That's not bad, but look at how much you can get done with the Stroop effect. And it's a big effect. You're guaranteed to get it. So which one would you recommend? Now, it's likely that only the project based on the Stroop effect is going to fit Angela's time and budget, kind of based on everything that we calculated. When you know how many people you need per group, you can start figuring out how much it's going to cost you for participant payments. You're going to be able to figure out how much time it's going to take you. And because of that, here's the other thing. She may want to do a replication or a follow-up study. If it only takes her 2.5 weeks to collect her data, that gives her enough time to run another study. So this is probably going to be your best bet. Norm of reciprocity would be second, but yeah, sunk cost effect, don't do it. 16 weeks, that's like 4 months of collecting data. Okay, so can you kind of see how precision for planning can be really useful? I hope so. All right, so now we're going to take a quiz, and then we'll start talking about correlations. Don't worry, this one's not too bad, I hope. Feel free to ask me questions. There's no math here. Why are you laughing? Oh, you're crying? Oh, don't cry. You're going to be okay. You're very welcome. You're welcome.
I swear I'm gonna give you one of these days. Maybe before I leave.
Well, I'm over your drink. Your
Your
drink is important.
Get out of the state.
What's wrong with Missouri? I like some aspects of Missouri. I think every place has its own set of problems, and it's just a matter of figuring out which ones you can live with and which ones you can't. I'd rather live with the problems that Missouri has than the problems that Florida has. Florida's crowded. I don't want that. Yeah, I'd rather have a hurricane than a tornado, because at least a hurricane I can outrun. Sometimes I myself, there are hurricanes that will sometimes run like maybe 10 miles an hour. I'm like, maybe I can't run that fast, but sometimes they barely move, and then I'm faster than a hurricane. Got a question?
On number 3.
Number 3, okay.
You on D, you said not the correct answer.
Yes, you have no reason to pick it. I am telling you it's not the correct answer. Nobody's head exploded. I actually had my research methods instructor occasionally like to give extra credit when we were in undergrad. And one of the ones she did for extra credit was, what are the team colors of Florida State? And one of them was orange and blue. And she wrote, you better not guess this one. That's our rival school. Yes, please don't pick the one that I specifically said is not the correct answer unless you are choosing malicious compliance for the day. Great. Does anybody need a few more minutes? Okay, great. Yeah, what's up? Let me take a look. Which number are we, what number are we talking about? 10? Okay.
Doesn't it, so we have golf with the population and stuff too, right? That's not-
Okay. Okay, so pay attention to what that says at the end of the question. The approach is easy. It doesn't really depend on sample size. What is the number one way to increase your power? Sample size. So clearly that one is not correct. Does that help? Okay, cool. Is everybody good? Isabel, Clelia, do you need more time? Okay. Oh, Joanne, you too. I'm sorry. Please don't be upset at me for asking. It's not like I was going to move on without you. I would never do that. We're a team. We don't leave team members behind. Yeah, you done? Everybody done? Okay, one more? Okay, that's cool. Okay, you think you're done. Okay, are we ready to go over it? Okay. All right, publication bias is A, the tendency to publish positive results, meaning they got a significant effect, but not negative results. Okay, number 2, in the null hypothesis significance testing approach, obtaining a p-value of less than 0.05 is taken as evidence that the researcher's hypothesis is supported. Unfortunately, D, researchers can engage in p-hacking, adjusting how they run the study and analyze the data until they get the desired p-value, regardless of the truth of their hypothesis. Number 3, according to Ioannidis, scientists have made 3 key mistakes: not replicating enough, putting too much emphasis on p less than 0.05, and having tremendous publication bias. What do we know about the effects of those problems? A, ionitis is essentially correct. Attempts to replicate previous findings have shown that too much of what is published is not very reliable. It's either not significant, or if it is, it's underpowered. Planning for precision is all about selecting a sample size that will provide a desired, so this would be all of the above. We want a certain level of power. We want a certain chance of type 2 error because that relies on power. And then we want that target margin of error. To be more precise, A, you need more participants, but each next step in precision, the more precise you want it to be, the more precise those participants are going to have to get. And by the way, notice this is exponential. It is not a linear relationship. This is an exponential relationship. Okay. Number 6, the open science movement seeks to help fix the replication crisis. How? All of the above. Okay. Whitney is planning a replication of a previously published study. The original study found a Cohen's d of 0.7 with a margin of error of 0.65. What considerations are important for Whitney in planning a sample size? All of the above. It is all of the above. She needs to have at least, at minimum, the sample size of the original study. She needs to have a margin of error that is smaller than the original study because odds are pretty good. The original study is underpowered. And then additionally, she needs a margin of error that is less than half as big as the expected effect. Alice conducts a simple independent group study with 20 participants per group, 40 participants in total. Steve examines the same research question, but uses a paired design within subjects. Steve also has 40 participants. Both studies have the same dependent variable. Based on this, C, Steve will probably have a smaller margin of error. Paired designs yield smaller margins of error. For a paired design, power and precision are related to sample size and to the correlation between repeated measures. The higher, the better. So A. Finally, in the null hypothesis significance testing approach, one plans for power. In this approach, B, power is the chances of not making a type 2 error. It is the chance of rejecting the null if the null is false. You do not want low power, and power absolutely depends on sample size. All right. Yeah, what's up?
I have a question, right? So like, let's say I want to like replicate a research, right? And like, let's say the original research had like independent space, and let's say like I wanted to do it, and I decided to do like a one paired design.
I wouldn't want to do that. That's it. Well, that's not a direct replication.
So that wouldn't work.
I mean, you can, but you have to acknowledge that there are things that you will have to consider in taking a taking a between groups design and turning that into a paired design. There are things you will have to take into account that the original study never had to take into account. You're going to have to think about things like counterbalancing. You're going to have to, if you want to replicate my thoughts are, and obviously other people may believe differently, go with what was originally done. And then if you get a good result from the original design, follow up with the repeated measures design and see if it holds true, and you get a bigger effect when it's repeated measures. But start with that direct replication first. Replicate as much of it as you can before you start trying to change things and extend it. Yay! We've got 20 minutes to talk about correlations. Very cool. And by Thursday, you'll know how to calculate them. And I promise it's not that bad. Do y'all remember Z-scores? Vaguely? If you remember how to okay, have you seen dodgeball? If you can dodge a wrench, you can dodge a ball. If you can calculate a Z-score, you can calculate a correlation coefficient. Okay, so we are going on to chapter 11. I think you're gonna like this one. People like talking about correlations. So we're going to start by talking about scatter plots. We're going to calculate Pearson's R, the correlation coefficient. And because this is estimation and because we can't not, we've still got to talk about the confidence interval on our correlation coefficient. So if we were to replicate this, what would the true population correlation coefficient be? Of course, we have to talk about correlation and possible causation, and then actually interpreting the correlation coefficient. So we're going to start by using scatter plots. One of the nice things about correlation is that when you're looking at a scatter plot, you can usually make a pretty good guess about how strong your correlation coefficient actually is. So I want you to think about, let's say that we wanted to look at the relationship between body satisfaction, which is plotted here on our x-axis, and well-being, which is plotted on our y-axis. Here, higher scores mean higher values. So a higher score on the x-axis means greater body satisfaction. Here, higher scores on our y-axis indicate higher self-report measures of well-being. So each point on our scatter plot represents one person's data point, their x coordinates and their y coordinates. This helps us determine a position. So this person is about a 2 in body satisfaction and pretty close to a 4 in well-being. So body satisfaction is on a 1 through 5 scale, well-being is on a 1 through 7 scale. And as you can kind of see here, there does seem to be a relationship of some kind. As body satisfaction increases, in general, well-being also tends to increase. But I want you to notice here that these aren't falling on a perfectly beautiful straight line, are they? They're scattered. And because they're scattered, what you're actually looking at here, this is a correlation of 0.47. And some of you might actually be surprised by that, because normally when we think of 0.47, we don't think of that as a pretty strong correlation, but it actually kind of is. There is a moderately strong link between high body satisfaction and high well-being. And I will say this, when you are dealing with humans, remember that all of us vary, all of us are different. You are generally not going to get a correlation coefficient of 1 if you are doing work with people. When you get a correlation coefficient that's pretty close to 0.5, when you're talking about people and you're talking about psychology, this is a massive effect. Okay. So here are a couple of things to kind of keep in mind. So even with a strong correlation, if it's not 1, so a correlation coefficient of 1 means that all of the data points are going to fit on a line and there's no scatter. So even with strong correlations, we are going to get scatter. Friendly reminder, correlation does not imply a causal relationship. We can't say that high body satisfaction caused high well-being or that high well-being caused high body satisfaction. You can't. So remember, when we're talking about correlations, you've heard me say this a lot, we are not manipulating anything. You weren't there to manipulate these variables. So you don't know which one came first. Because you don't know which one came first, you can't actually make a cause-effect relationship here. You can say that they influence each other. You can say that they're associated with each other or that they're related to each other, but you can't say they cause each other. You didn't manipulate any of this. You're just measuring what's already there. I didn't mean for that to be as tiny as it was. I thought it was going to be noisier. Y'all have no idea, when I was, I think my first year teaching, I had a set of identical twins and they were in 2 different general psychology sections that I taught, and yet both of them sneezed 7 times in a row, every time. Just one right after the other. Oh, all right. So correlation is largely measured through Pearson's R. So what you're looking at here, we are looking at sample sizes of 50 across different correlations. So here's what I want you to notice. So notice that there's not really a lot of scatter at 0.9 compared to 0.6, 0.3, or 0. So here, we don't really have as much scatter. So generally, Pearson's R, so the correlation coefficient measures the linear component of an XY relationship, and it takes its values between -1 and 1. Here's what's really important here. If you've got something that isn't linear, if you've got a relationship that is not linear, this will underestimate your data. It will not accurately describe your data because we only have 2 variables. What can we do with 2 variables? The only thing that we can do is connect a line. So because of that, we're only looking at the linear relationship between X and Y. If you have something that is not linear, if you have something that curves or is exponential, it's going to underestimate that relationship because it's looking for a line. So for any XY relationship, we need to see the scatter plot. And R can be helpful. So some of you might be surprised that the scatter plot still looks like this and it's 0.9, right? Here, we may, I don't know, this actually kind of fits for me, but here's where it gets a little tricky. Once you get to 0.3 or lower, these don't really look all that different from each other, do they? This is where it kind of gets tricky. And that's why looking at a correlation coefficient can be helpful, but looking at the scatter plot is important too. And I would say one of the best things you can do is look at scatter plots and start eyeballing correlations. So here's the thing. You can actually, one of the things you can do is try to draw a line that fits best through all of the points. By the way, that's basically what regression is. Regression is when you take a correlation coefficient, you basically try to draw a line of best fit through all of the data, and you try to make predictions of other data points based on this regression line that you've drawn. So here, we can actually draw a line through all of this data, and it looks like it would fit pretty well. You can do it with 0.62, but by the time you get to 0.3 or 0, it's harder. So here, you can get a better idea of strength with a regression line in the scatter. So here's R of 1. This is, look, there's no scatter. It is a line. It's gorgeous. You're never going to have data that looks like this. I'm sorry. I hate bursting your bubble. You are dealing with people. People are wonderful and complex. You are never going to get a correlation of 1. Here's -0.6. So one thing I will mention, all of the relationships that we've talked about so far are positive. As X increases, Y increases. But we can also have a negative correlation. As X increases, Y decreases. So an example of this might be that how much you practice is shooting free throws is negatively correlated with the number of mistakes that you make. So the more that you practice the more that you practice free throws, the fewer times you should miss. As one goes up, the other goes down. So here, we've got a beautiful correlation of 1. This is what it would be like if the world were perfect and everything were fair. You don't live in that world, neither do I. Here, we have a negative correlation of -0.6, and here is our 0.9 correlation, and this time I've actually added the regression line. So a regression line, I'm going to move this microphone because I'm going to point. So I want to make sure people still hear me. So the regression line here, what you're basically doing is you are trying as much as possible. So notice that each of these points has a certain distance from the line. right? So the distance from this one to the line is here. Here's one, this one falls right on the line. Regression is basically finding out the line that reduces the distance for all of the points, the distance between each point and the line as much as possible. This produces the line of best fit. If we picked any other line, the distance between each of these data points and the line would be larger. So this is where we get the minimum amount of distance for all of the points and their distance from that regression line. And you can basically make predictions based on that regression line. So if I know somebody's X, I can basically pull up that line and assume that their value on the Y-axis will be right on that line. Now, it's not perfect. There might be some variability there, but this is the line of best fit for a reason. So the regression line tells us what Y value is most likely associated with an X value that we're interested in. So correlations are useful because they're the foundation for regression. They allow us to make predictions. So now I want you to look at two nonlinear relationships. And this is just my reminder to you. Pearson's R only examines linear relationships. So folks, here's some beautiful data. It's between room temperature and rated comfort. Guess what this data tells us? We have a peak preferred temperature here. And as we move away from that, we become more uncomfortable. We don't like it when it's too cold, and we don't like it when it's too hot. This is a curvilinear relationship or a quadratic relationship. It's a parabola. So here's the thing. If I drew a line of best fit through this, it's going to be straight here. It's going to underestimate the relationship that I actually have. Here, we have a driver knowledge test and high school GPA. Here, it's kind of clear that as long as you have a basic level of understanding, everybody kind of maxes out on the driver's test. If you're kind of struggling with school, like a 1 or a 2 GPA, you're probably not doing very well on the test. And of course, nobody in this sample has a 0 GPA. I have yet to meet a person who has a 0 GPA. So here, we have a curvilinear relationship between room comfort and temperature. And then we have scores on a test topping out around 30. Folks, this is a ceiling effect. Almost everybody is getting a perfect score. Now compare that to a floor effect. If I had a floor effect, where would all my data be? At the bottom. So here's the thing. If I tried to draw a line through best fit, if I look at the correlation coefficient, it's 0.3. That means that the line of best fit kind of looks like this. Here, it's 0.76. It kind of looks like this. But this doesn't actually appropriately characterize the data that we have here. So if you have nonlinear data, don't talk about correlation coefficients. Okay. So we can actually eyeball a scatter plot to figure out what our correlation coefficient is, and not just in the way that we did earlier. The tightness of the points to an imagined line can help us actually eyeball R. The problem is that when you get more scatter, it's kind of hard to figure out where that line is. So another option that we can actually do is use a cross through our means. So here's what you do. So you basically draw a cross in the middle of your scatter plot. So here is the mean value of our X variable. So that's what the vertical line is. Here is our mean point of Y. It is the mean of our Y variable. So here's what we do next. So here we have 4 different quadrants. So here we have people who are low in X and they're low in Y. Here are people who are low in X and high in Y. Here we have people who are high in X and Y. And here we have people who are high in X, but low in Y. So here's what we want to focus on. If we have a positive relationship here, if this is a positive correlation coefficient, we should have more data points in the high and the low section than the mismatched sections. So more matched than mismatched would suggest a positive correlation. More mismatched than matched would indicate a negative correlation. And if you have an equal number in all 4 quadrants, what is your correlation? A 0 or near 0. So mostly matched or mostly mismatched actually points to a stronger correlation. Ones that are kind of scattered in all 4 quadrants, like this one, actually will indicate a weaker correlation or no correlation at all. So this is another way that you can kind of think about this. Now, if we go back to our nonlinear relationships, you can see that if we do that quadrant here, we're kind of in a weird situation. Here, the correlation is weak because we basically, for the most part, have almost an equal number of people in each quadrant. Now, it's not perfect. We have more matched than mismatched, but in general, the numbers are pretty similar. This is 4 data points, 3, 5, and 2. They're all pretty close to each other. So because of that, we get a correlation of 0.3. There's an equal distribution. Here, we've got more matched than mismatched. And then we don't know anybody who gets at least a B average GPA and is failing the driver's knowledge test. I wonder why. Is it probably because people who are motivated to do well in school will also probably study for a driver knowledge test? Yes. So there's nobody in our mismatched quadrants. So in this case, it actually overestimates the relationship. It looks strange because there's no data here. Okay, so that's another way that you can kind of think about it. So we've got 5 minutes left. So I'm going to show you a formula. So do y'all remember the Thomason critical thinking study that we talked about when doing paired designs? Just a reminder. So he basically looked at 12 different people and they studied critical thinking with a pre-test, post-test design. Now, here's the thing. Remember that when you're doing a paired design, the correlation between your pre-test and your post-test measure is really important. And generally, what we're going to find is that our pre-test and our post-test scores have a high correlation. Here's the data. So here is our pre-test score. Here is our post-test score for all 12 participants. So what you're actually going to notice is that this corresponds. Notice that there's very little scatter. And you could argue that part of that's because there's only 12 people, and I'm pretty sure that might be some of it. But in general, people who do well on the pre-test do pretty well on the post-test too. And we get a 0.89. So here, if we kind of do our battle of the quadrants, we have more that are matched than are mismatched. Now, if we want to get this correlation coefficient, if you want to figure out how we got this 0.89, this is where we're going to need our z-scores. Yep, I'll show it to you, but I'll start on that slide so don't feel like you have to write anything down for this, but I want you to look. You only need z-scores to figure out a correlation coefficient. So just as a reminder, your z-score for an x variable is a particular score minus that variable's mean over its standard deviation. That's a z-score. So you're basically going to get a z-score for all of your x variables or all of the scores at x, and then you're going to get the z-scores for all of your scores on y. So ESCI can do this for you. It can help you with your Chapter 11 handout. But here's how you calculate R. Folks, this is it. You add up, so you multiply your z-score for x and your z-score for y for each person, add them all up and then divide it over the number of people minus 1. That's all you have to do. Calculate the z-score, multiply each person's z-score for x by their z-score for y, add them all up, and then just basically put that over your number of people minus 1. Now, there's another way that you can do this, but it's more complicated. Focusing on the z-score solution is actually pretty easy, now that you know how to do it. All right, folks, that is all I have for today. So the Chapter 11 handout is just a step-by-step process for calculating the correlation coefficient and producing the confidence interval for it. You are welcome to use ASCII or Excel. You can also do it by hand if you wish, and we'll talk about how to do that next time. So you can actually start doing a little work on it right now that you know the formula for Pearson's R. So, folks, thank you so much. Have a great day. I will see you next time.